All right. So the last few questions we dealt with seeing the consequence of the geometry of special relativity in the time domain, temporal. Let's see what it's like in the spatial domain. This time we'll run into the Lorentz contraction. All right, so our statement reads, a Lincoln Continental is twice as long as a VW Beetle when they are at rest. As the Continental overtakes the VW going through a speed trap, a stationary policeman observes that they both have the same length. The VW is going half the speed of light. How fast is the Lincoln going? What we know is that the Lorentz contraction will happen by a factor, by the Lorentz factor. So L is equal to L naught divided by gamma, where gamma is the Lorentz factor that we've been using. A quick note on this is that the Lorentz contraction can only happen in the direction of motion. So not perpendicular, those directions don't contract, only the direction of motion does. So be aware of trick questions like that. All right, so at rest, what we see is that the Continental at rest is twice the length of the VW bug at rest. But when moving, the Continental is the same length as the VW bug. Okay, so let's set up the contraction statement for both of them. Here we see that LC naught over gamma C is equal to LV naught over gamma VW. Again, when they're moving, the contracted length are equal. So we use that contracted length to set the two equal. That being said, now we can substitute in what LC naught is, which is 2 LVW naught. And as you see in the next step, both these factors cancel. So from this, we can find out from the Lorentz factors what speed they're going. So solve this thing for gamma C. Okay, we do that here. We see we get 1/2 times 1 over gamma VW. In the VW, again, we see that the C's cancel. We like that. Easy enough to deal with. Get rid of the speed of lights when you can. And then we're just left with a fraction, 3/4. Again, you can break up that square root into the numerator and denominator, hence the 2 there. So what we see is that 1 over gamma is equal to the square root of 3 over 4. Okay, so that's what we recapped there. But we also know that 1 over gamma C is equal, where gamma is the Lorentz factor, is equal to 1 over the square root. So we just multiply by the reciprocal, save ourselves some time. So anyways, the 1 over gamma is equal to the square root. Cool. And this within this square root is the v that we want. So let's solve for vc. Square both sides. Move everything over. So switch the position of the parentheses. And then once we do that, take the square root after we plug everything in. Note that we left the 1 over gamma c term as a fraction for this specific reason. And now we're going to sub in the fact that we found that 1 over gamma c was equal to square root of 3 over 4. So once that thing gets squared, we see that we have 1 minus 3 over 16. And then 1 is to 16 over 16, so 16 minus 3 is 13. Easy enough, algebra away. Take the square root of both sides. We see that we get VC over C is equal to root 13 over 4. Multiply the C over, and we get the speed we need. As you see, that is going to be, let's see, 1/2, that would need to be 2. So yeah, this is greater than 1/2 the speed of light, which is what they were traveling at. So we're doing pretty good. Pretty clever use of the Lorentz contraction, I would say, but nonetheless, algebra is your friend once you set everything up. The physics, of course, is in the setup. The algebra is where we make or break all the calculations. So with that, we'll see you on the next one.